Hello, I'm Neeraj. So in this part of the tutorial, I will try to explain that how we can solve the situations of aleatoric and epistemic uncertainties. So first of all, we will concentrate on aleatoric data uncertainties or aleatoric or data uncertainties. So in the case of aleatoric uncertainties, our goal will be to identify all the noises or random entries in the data and separate or isolate them from the actual data, so that when we train the model next time, it will give a better performance. So in the traditional way, when we train the model, what we do, we take the input data and then develop our model and train it for some level output or some regression values. But to apply the aleatoric or to remove the aleatoric data uncertainty points, we make slight changes in the model. We, instead of just predicting the output, we will predict two things: mean and variance. To predict the mean and variance, we have to design or change the loss function also. If we use the traditional mean square error loss function, then what will happen? Actually, variance in the case of aleatoric uncertainties will not be fixed. It will change according to the underlying data. If noises will be very high, variance will be very high. Means there will be a lot of uncertainties or variability in the variance. So whenever we apply the mean square error, we can learn the parameters of multivariate Gaussian with mean y and constant variance. But here variance is changing, variable. So in that case, we have to change the strategy and we will go for negative log likelihood. NLS. So here you can see that for each of the entry points I, we are considering the variance here and taking the log E of variance. So with this, when we minimize these loss functions, it will cover these variable variances also. Now the next point is how we can use this trained model to handle the aleatoric uncertainties. So after training this model, when we pass the data and after that we find that for a certain data point, if variance is very high, then we will isolate all those points from the model. Based on the variance score, we can isolate those points from the model, and that's way we can remove points like this. From here we can remove these points, we can remove. So this way we can remove the noisy points. So this is one of the simplest way to do this. To handle the epistemic uncertainties, we are using the ensemble of models. We will take the input data X, design the model 1, it will generate, train for same output Y, we will take another model M2. Similarly, based on our requirement, we can design the number of ensembles to fulfill our requirements, for example, and so on. Now, what are the process? How we can design this ensemble? So we are using two different strategies. First is random initializations of all those architectures. Second is by using dropout. But just be careful. Here we are using dropout with train and test both. So with random initializations, every time the system will get initialization value, different initializations value, because it is random. And again we are using the dropout and for train and test both. In general case we are not using the dropout with test because it generally results in the loss of some data, some values, and it affects the prediction scores. But here we are using both. So whenever we will get the cases like this, where there is no underlying data available, in that case we get scores, results, and when we plot those scores, mean and variance, then we will find that in all those cases the mean and variance plot will be scattered in a lot of different ways for such kind of data points. And for the data points where there is no problem, the mean and variance will be plotting will be very near to each other, means there is no problem in the data. So for all those points, like these points where they are scattered far away and so huge differences, we can ask to add more data for those regions. Only then the system can forecast or predict correctly for those regions. Now another thing, you should be careful when designing this kind of system. Don't make changes, means keep the hyperparameter of the system as same. So these are the things. Someone claims that due to ensembling techniques we will use a lot of models, it will consume a lot of time and create a lot of problems. So some shifted towards use of generative models, variational autoencoders, some selected the use of Monte Carlo simulations and Monte Carlo dropouts also. So there are a lot of different techniques generally people invented in this area. So in this tutorial I am just considering the basic techniques. Now we will try to understand how we can use variational autoencoder kind of architecture to check the epistemic uncertainty of a model. Actually, variational autoencoder is a generative model. It provides us some flexibility to add some creativity on the input data. That's why it is generative model. So let us see how it is working. When we take the input data and pass it through some probabilistic encoder, it generally generates mean and variance. After that, we apply some sampling strategy, take the sample latent variable. Actually, these sample latent variables are multivariate Gaussian distributions. So the probabilistic decoder actually takes those inputs and try to reconstruct the original images. But what happens, due to these sampling strategies, we get some space for creativity. Means if we provide some image, then as an output we can get some variations in the images. So this is the actual concept. If you want to know more detail about variational autoencoder, then you can watch my previous video tutorials on variational autoencoder. So now let us try to understand that how it helps us in modeling the epistemic uncertainty. Suppose you train this model for features of cat and dog. So system is trained for the features of cat and dog. So any variety of cat and dog image, if you provide and take the output like a sample latent variable output and pass it to some classifier or some any other ways, and then take the mean and variance score of the predictions, then you will find that for all kind of cat and dog images, it is very much near to like those means variance will be too low and mean will be also near to. But suppose if you pass an image of apple, then you will realize that the variance and mean is highly deviating, because this step, like which extracts the mean and variance and then calculate the sample latent variables, so a huge variations. And if you such kind of things you observe in your result, then you can be sure that in the case of according to the epistemic uncertainty philosophy or measurement technique, if all results are very much near to each other for all kind of cat and dog images, and for other results, for other kind of images like for apple images, it is too far from the predictions result, then model is a good model according to the epistemic uncertainty test. So this is the way we generally test the model uncertainty by using by using the variational autoencoder. The only thing which is different from the traditional ensemble based testing is like here we are using the single variational autoencoder instead of taking the multiple ensembles. So this is the only difference, but still you will have a lot of issues that we generally face with variational autoencoder training. So now we will try to go through another topic. Now we will try to discuss about the reliability of the model, like model calibrations. To measure the model calibrations, we generally use the Brier score. Brier score BS is given by 1 by n and is equal to total number of events. And it can be given as difference square of difference of FT, which is a forecast probability, and OT is the actual output of the event. So from this example it will be clear. So in this case we are just considering the binary event for which output will be either 1 or 0. So output is either 1, 0, 1, 1. So we are taking the 4 events like n equal to 4. So in this case we have two models, M1 and M2. So for M1 models, for each cases we got the probability score for FT, forecast probability. In the case of first case it is 0.5, second case 0.5, third case 0.4 and fourth case 0.8. So when we put all those things, we get the Brier score 0.225. Similarly for model M2, we have 4 forecast probabilities. So based on that, when we put those things in the Brier score computation, then we got the model score 0.4675. So in this case, we will assume that we can easily understand that model M1 is better than M2, because in the case of Brier score, the model whose Brier score is near to 0 is considered as the better model, means more reliable model. We generally use one more scoring mechanism to achieve the model calibration. So that is known as Brier skill score. So Brier skill score, in that case we use the reference model. So in that case Brier skill score is equal to 1 minus Brier score of the actual given model and then Brier score of some reference model. So in this case, if we get the Brier skill score greater than 0, then we consider that our model is better than the reference model. And if BSS is equal to 0, means there is no difference in the with respect to reference model in the case of calibration. And BSS equal to 0 means our model is the worst model, means it is poor than reference model. So these are the two major basic measures are used to measure the model calibration score. So thus in this tutorial, actually we have considered two major things, uncertainty and reliability. Under uncertainty, we have discussed about aleatoric and epistemic uncertainty, and under reliability we discussed about model calibrations, and we tried to explain those things through uh, basic approaches. In the next part of the tutorial, I will try to come up with some latest algorithms in this area to capture the trustability of the model. So thanks for watching.